The engine air intake provides a relatively distortion-free, high-energy supply of air in the required quantity to the face of the compressor. A uniform and steady airflow is necessary to avoid compressor stall and excessive internal engine temperature at the turbine. The high energy enables the engine to produce an optimum amount of thrust. Normally, the air intake duct is considered to be an airframe part, but the duct itself is so important that when considering engine performance, it must be included in any discussion on the complete engine. Air intakes are designed either subsonic or supersonic configurations. Those that maintain optimum airflow condition up to a high subsonic speed are called subsonic intakes, whereas those which are also required to operate efficiently at airspeeds exceeding Mach 1 are called sonic intakes. For a typical gas turbine engine, the velocity of the airflow at the compressor inlet is normally less than 0.5 Mach. This ensures high compressor efficiency. So while designing the air intake, our main goal is to bring the speed of the air at 0.5 Mach at the face of the compressor. We will see how this requirement is fulfilled for both subsonic and supersonic configurations. The aircrafts which fly in the subsonic regions needs to have a subsonic intakes. The subsonic intakes are designed as a divergent duct, so that when the air enters the engine air inlet at point A, it will be around 0.75 Mach. Now recall that whenever a subsonic flow passes through a divergent duct, as the area of the duct increases, the pressure increases and the velocity decreases. Hence, when the air has reached point B, the velocity of the airflow has been reduced to 0.5 Mach. This ensures high compressor efficiency. The aircrafts which fly above speed of sound needs to have a sonic intakes. The sonic intakes are divided into two portions. The first portion constitutes a convergent duct, while the second portion constitutes a divergent duct. When the airflow enters the point A, it has a speed of 1.5 Mach. Now we need to reduce the speed first to make it subsonic. For this, the sonic intakes utilizes a convergent duct. Now recall that whenever there is a sonic flow through a convergent duct, then as the area of the duct decreases, the pressure of the airflow increases and the velocity of the airflow decreases, so that when the airflow reaches the point B, its speed has been reduced to 0.9 Mach. Now here is an important thing to remember. The airflow has become subsonic now. If we continue using the convergent duct ahead of point B, then instead of decreasing the speed of the subsonic flow, the speed will be increased. Since we know that a subsonic flow through a convergent duct increases the speed, so at this point, in order to decrease the speed of the subsonic flow, we will use a divergent duct ahead of point B. As the air flows from point B to C, the area of the duct increases and the pressure of the airflow increases as well, but the velocity starts decreasing. At point C, at the face of the compressor, the airflow has reached 0.5 Mach. This ensures high compressor efficiency. For more training videos, keep watching the Hash Academy. Let us discuss the design requirements for engine air intakes. So there are basically three requirements that the air intake must fulfill. Number one, the air intake must recover as much of the total pressure of the air as possible and deliver this pressure to the face of the engine compressor with the minimum losses. Number two, it must deliver the air uniformly with as little turbulence and pressure variation as possible. And number three, as far as the aircraft itself is concerned, it should keep aerodynamic drag to a minimum. For more training videos, keep watching the Hash Academy.